Hello and welcome to this practical training session for the Copernicus Marine Service Workshop MarineData4Africa. My name is Ergane and I'm going to be your trainer for this session. So this Python training session for this workshop consists of 4 Jupyter Notebooks, 1 introduction and then 3 exercises. This video is about the 3rd notebook, so the 2nd exercise, in which you will learn about the Congo River discharge in the Atlantic Ocean. So these are Jupyter Notebooks. They consist of text and code, Python code cells. And to run a cell, you have to click on the arrow here on the top menu, or you can also use the keyboard shortcut Shift and Enter. So we are going to study the Congo River and its discharge in the Atlantic Ocean. The Congo River is one of the most important rivers in the world and in Africa, of course. It's one of the biggest river, longest river, and it's also one that has the largest discharge volume. The river basin drains 9 countries, although the majority of the river is located within the Democratic Republic of the Congo. And so because it's such an important river, it has an effect on the ecosystems, the wildlife, and also, of course, on human activities. And for example, the DRC's economy relies on the Congo River for fields such as navigation, drinking water, and hydroelectric power. The Congo River does not only have an impact on the land, but also on the Atlantic Ocean, because the river mouth, especially when the river from when the water from the river reaches the ocean, the fresh water affects the estuary. And the river carry nutrients from the land, but it also sometimes carry products like that bring pollution into the ocean, and therefore monitoring the river discharge of the Congo in the Atlantic Ocean might be very important. In this exercise, we're going to use the Copernicus Marine Service products, so observation and models, to see how we can monitor the Congo River discharge in the Atlantic Ocean from this data. So about this data, we're going to study the river discharge from the following parameters. So we are taking the sea surface temperature and the salinity, because the salinity will help us see the impact of the river on the river mouth, because the fresh water coming from the river decreases the salinity around the river mouth. And the chlorophyll, we are also going to study the chlorophyll to see how, because as I've said, the river brings nutrients, and the nutrients attract marine wildlife, and we can see such marine wildlife from the chlorophyll, because when the phytoplankton carries out photosynthesis, they use chlorophyll. So we can estimate the amount of wildlife thanks to the chlorophyll parameter. So these variables, we're going to subset them so that to study them in this region. So here are the coordinates of the region that we're going to study. The depths are from 0 to 100 meters, and we're going to observe the evolution of these parameters from February to April 2020. So where do these parameters will come from? We are going to study them from both observation and model products. So regarding temperature and salinity for the model, we are going to take them from the Global Analysis Forecast Physics model. For all the products that I'm going to present here, you can find the link to the web page. So here, for example, you can have access to the description of the model. You can also access the data here. You can also access the documents of the product. So the documents that describe the products and also that describe its quality. So this was for the temperature and salinity model. We are also using the biogeochemical model so as to study the chlorophyll. To study, for the observation, we're using the ocean color observation. That is for chlorophyll observation. And finally, for the observations of SST, we're using this product. Again, you can have for all these products the web page and their documents. So all the data that we're going to use in this exercise, they have already been downloaded for the training, so you don't have to download them. They are located in the data folder here. You can find everything you need. But in case you want to download some other data, like to study another region or another period, you may want to have a look at the introduction notebook as it explains the different ways you can download the products from the Copernicus Marine Service. This notebook will also show you how the NetCDF files are constructed and how you can use Python to handle these NetCDF files. So if you're not familiar with these products, you may want to have a look before starting this exercise. Okay, so we can now begin to study to use Python and to study the Congo River discharge. Just like any other Python code, we need to set up the notebook with the necessary tools. These are the libraries that we're going to use: NumPy, Xarray, Matplotlib, and Cartopy. Here you can find the links to the library's webpage, and it will describe their functionalities, what you can do with them, etc. So if you're interested in that, you can have a look. And now we can start running the cells. So here the first cell will import the libraries. Then we're loading the products. So as I've said before, the data are stored in the data folder. And so the first step will be to define the paths to the NetCDF files and then to open these files and store them into data. Python variable, sorry. So we're running the cell. And if you want to have a look at the products, dimensions, and variables names, you can use the following command. So you just have to put the name of your Python variable into a cell and run it, and then you will access its dimensions, its coordinates, and its variables. So here for the observation SST, you have the variable analyzed SST. You can click here on the show hide attributes, and you can have access to its units, for example. So we can see here that the unit is Kelvin degrees. So we're now all set to begin our study. We have the physical model, the biogeochemical model, the observation SST, and the observation bio variables. So we can begin our study. The first thing that we're going to do is to plot the evolution of the salinity, because as I've said before, when the fresh water from the Congo River reaches the river mouths in the Atlantic Ocean, the salinity strongly decreases because of the fresh water. And this is what we are going to see. So this first cell will plot the evolution, and I'm going to do to explain each line and what it does. So the first line here defines the figure and its size. Then we define the projection of the map. We add the coastlines. We add the grid lines, so the longitude and latitude, and we remove the labels on the right and on the top. We add the land mask. We set the extent, and finally we add the title. So these are for the characteristics of the maps. Then we can plot the data. We are plotting, so here the salinity. This is the variable we're using. We define the values of the color bar, so the values will go from 10 to 30. And we're also defining the color map, so the colors we want for the salinity to appear. Finally, we add the legend and we save the figure, so the figures are all saved in the out directory here. So we can run the cell. It might take some time. And so when the calculation is over, you'll see that the hourglass does not appear anymore. The little star here does not appear either. But you can see also that not any figure is displayed. That is because of the last line here where we close the figure, and therefore it does not appear. That is because we have chosen not to plot any figure, because we don't want to look at each figure for each date time, but we would rather display an animation and to see how the salinity evolves from an animation. So to do so, we are going to import the modules that we need. You can see that we have saved our data. Well, the names are sal date. So then we're going to find all the figures that start with this name, and then add them to a list, and finally make an animation and display it. So here is the animation that we have created. You can see the color map we have defined, the color bar. You can see we have no labels on the right and on the top. We have the title. We have the land mask and the coastline. So this is all the characteristics we have defined in the code. And so we can see here, we see very well the plumes of the river. We see very well that the the river mouth is affected by the river discharge. We can see that the salinity varies. Like some days it's higher than some other days. And so that's it for the animation. We're going to see the evolution of the other parameters, and we're going to analyze how they are correlated with the salinity and therefore with the river discharge. So the two parameters we have chosen to use are the temperature, the sea surface temperature, and the chlorophyll. So this is what we're going to do. We're going to plot the same maps, but for so the salinity, the model and observation temperature, and the model and observation chlorophyll. This is what this code is doing. So we are defining several axes, and we plot here the salinity, the temperature from the model, the temperature from the observation, the chlorophyll from the model, and finally the chlorophyll from the observation. We are not using the same function here because we had used the pcolor function before, but this function takes quite a long time, and because we are plotting a lot of maps here, we will rather use the contour F function. So we can run this cell, and and so for the contour F function, you need to select the bins of the color bar you want. So that's you don't only set the min and max values of your color bar, but also all the bins. You can see in the out folder that the figures that we are generating, their name starts with sal, temp, chlorophyll, date, and we can see that they are being created now. And so again, when the calculation is over, the figures do not appear, again because we have used the line close. Instead, we're going to display an animation, so we are running the same kind of cell code that we did, and so here is the result. So you can see that the color bar is indeed well, it's using bins and it's not continuous. So regarding the chlorophyll, we can see that the patterns of the chlorophyll evolution really match with the evolution of the salinity. We can also see that the model slightly underestimates the amount of chlorophyll compared to the observations. Regarding the temperature, the results are not as obvious as for the chlorophyll. The temperature doesn't seem to be affected by the river discharge, and that may be because some other phenomena are at stake in the region, such as upwelling, for example. And so, we can still see that the chlorophyll is affected, so that the wildlife is affected by the river discharge. The first exercise I'm proposing to you in this notebook is to try to see the evolution of some other parameters, because if you see, for example, if you see the bio model, you can see that it contains many variables, like the nitrate or the pH, for example. And you may want to see how these parameters are affected. We have seen that the temperature doesn't seem to be affected. However, the chlorophyll really was affected by the river discharge, and you might want to see how the other parameters are correlated with the river discharge. So now we're going to study to estimate the extent of the river discharge effects on the ocean surface. Therefore, we're going to study 3 regions that I'm going to define. First, let's see this region. So these will be 4 regions. We will have 1 point, 1 small region, so 1 small square, and then a bigger square. So this is the point. We have defined its coordinates here. This is the small region. We have defined its coordinates too. And finally, the bigger region. So what we're going to do now is to interpolate the products that we have on this point, and also on this small region we're going to plot the average parameters in this region and also in this bigger region. So this way we are going to see if the river discharge affects like just a point very close to the river mouth, also a small region, and if it also affects a bigger region. So we are running this cell. This cell is used to calculate the mean parameters. So here we can see that we calculate the mean over the longitude and latitude parameters. And then we plot the time series of the different parameters in the different regions. So in blue here we have the time series of the salinity at the point. We have the average in orange, we have the average salinity in the small region, and then in red the average salinity in the big region. We have done this time series for the salinity, the temperature, and the chlorophyll. And so we can see that so these are for the, I didn't mention it, but we have plot this series for the model, not the observation. We can see that the evolution of the parameters in the small region and at the point are very similar. Like they are, the lines are very close to each other. However, regarding the big region, for the salinity, we can see that it's not as much as affected as for the smallest regions. The temperature seems to follow the same evolution, but it's still slightly further than the other lines. And finally, regarding the chlorophyll, we can see that the big region is not affected at all by what's happening in the river mouth, and therefore we can conclude that the Congo river discharge only has a local impact on chlorophyll. We're going to plot the same figure, but from the observation products. So here. And for the observation products, the results are slightly different. It's not the correlation between the parameters are not as obvious as they were with the models. We can see that the parameters sometimes drop or strongly increased, but we can still see that the extent of the effects of the discharge is almost, well, we observe the same consequences on the three regions. It's not as different as it was for the models. And we can also see the correlation between the parameters. It's maybe more obvious with the models, but we can see that when the salinity increased, the temperature also strongly decreased. And we can see that right after the salinity increased, the chlorophyll also decreased. So an increase in the salinity means that the river discharge decreases, like there was less fresh water coming to the ocean, and therefore less nutrients probably, and this is why the chlorophyll decreased. The correlation between the salinity and temperature is not always obvious, but still we see here that they evolve at the same time, and that may be because of the river discharge, although as I've said before, there are all the phenomena occurring in this region, so this evolution may not be related to the discharge but to upwelling, for example. And then finally, I forgot. You can try to change the coordinates of the regions here, and to see if you see other evolution and if you see other correlation. Again, you can change also the parameters to see to study, for example, the nitrate that represents the nutrients in the water. You can also study the pH or some parameters to evaluate the pollution of the river, for example. And so our last section will be to plot to see the evolution in the deep ocean, and so not only on the surface. And therefore, we're going to plot an Half-Malay diagrams. Half-Malay diagram are diagram that where the axes are depth and time, and so we're going to plot again the salinity, temperature, and chlorophyll parameters, so as to see the vertical evolution, the evolution of a vertical slice. So here, regarding the salinity, we can see that the salinity strongly increased over this period. We can see that the temperature pattern really matches the evolution, like wherever the salinity increased, the temperature decreased. And we can also see the chlorophyll evolution, and we can see that when the salinity increased, therefore when there were less nutrients, less fresh water, and therefore less nutrients coming from the river, we can see that the chlorophyll decreased. So this is the end of this notebook. We have seen how the Congo River discharge affected the Atlantic Ocean. We have seen this phenomenon through the salinity, temperature, and chlorophyll parameters. But you can try to see the evolution of the other parameters if you're interested in that. So thank you for watching. There are other exercises about upwellings and cyclones, which also use Python and Jupyter Notebooks. So you may want to have a look at these notebooks if you're interested. So again, thank you for watching. I hope you enjoyed this video, and I will see you in the other exercises.